The next talk will be from id Software, where the speakers will describe how they approached achieving varied environments while maintaining 60 FPS, which was a key design goal for id Tech 7. This talk will cover the rendering systems that contribute to make the world of Doom Eternal feel more rich and dynamic, such as geometry caches, updated gore system, decaling, material compositing, and water rendering. Jean Geffroy is a principal engine programmer at id Software, where he worked on Doom 2016, Wolfenstein 2, Dishonored 2, Doom VFR, and Doom Eternal. His primary focus is on general performance topics and workflow improvements, tailored to game needs. He previously worked on character animation at Crytek, on Ryse, Son of Rome, and other CryENGINE titles. Yixin Wang is an engine programmer at id Software, where he works on Doom Eternal. Doom Eternal is the first title he worked on. Before entering the gaming industry, he worked at Google on Chrome networking. Axel Gneiting is a principal engine programmer at id Software, where he worked on Doom Eternal. His primary focus is on performance, engine architecture, and animation systems. He previously worked as an engine programmer at Crytek on Ryse, Son of Rome.
Hello and welcome to our presentation about the rendering in Doom Eternal. First, I wanted to mention that this was a huge team effort and we thank all our colleagues who helped. Before we go into details, I wanted to give a quick overview of what we changed since id Tech 6 and we can talk about today. We switched our rendering to fully forward instead of partially deferred. This was slightly faster in our tests. The engine still uses very few shaders and it's still a major advantage in iteration time and performance for us. In Vulkan we have just about 500 different pipelines. Our levels are much larger and the world is much more detailed. To facilitate this, streaming has been greatly improved and expanded, and we use low-level APIs on all platforms now. We even removed OpenGL from all of our tools and only use Vulkan there now too. And of course, we still want to achieve a stable 60 frames per second on all platforms at the same resolutions than Doom 2016. The first topic will be our new light binning solution. In previous id Tech 6 titles, like Doom, the approach used was clustered binning. We talked about this in our last SIGGRAPH presentation. Doom Eternal presented new challenges which required a new approach. The scenes are much larger now, which caused a lot of small lights and decals to end up in the same big clusters. Additionally, enemies now have light rigs and there are more projectiles in fights, which both cost even more small lights on screen. Artists, as always, also wanted to place more lights and decals in general to increase fidelity. We also wanted to move the binning to the GPU to reduce CPU load. The solution for this is a new hybrid of cluster and tile binning. As an example, we will be looking at this scene from the Moscow level. This is a debug view of the decals and lights that are visible after CPU culling. It shows the bounding boxes of decals in green and those of lights in white. In total, there are about 1100 decals and 150 lights. Here we see what the light overdraw of the same scene looks like with clustered binning. Red means there are over 20 lights and decals to be considered for those green regions. Blue, on the other hand, means only few lights or decals are binned. And this is what it looks like with our new hybrid binning. As you can tell, the overdraw is much reduced, which naturally improves performance. The tile binning part of the algorithm was inspired by improved culling for tiled and clustered rendering presented by Michael Trobot at SIGGRAPH 2017. A problem with the approach proposed in that talk for us was that we have thousands of lights or decals in a lot of scenes. With those amounts of objects to bin, the hardware rasterization tile binning becomes inefficient because of the amount of stencil state changes. On top of that, our budget for GPU binning to actually improve frame time in all scenes was about 500 microseconds on Xbox One. We decided to instead write a rasterize implemented as compute shaders. For simplicity, the only primitive that we raster are hexahedra like boxes or pyramids. Other shapes would be possible with this approach, but because there is also early rejection in the lighting processing, we expected diminishing returns from this. To make this fast enough, the resolution is quite low. The rasterizer also needs to be conservative, otherwise lights would incorrectly be rejected. This has many edge cases, as seen with a couple examples on the right. In our experience, artists are able to find all the ones you miss. To be precise enough far away from the camera, especially for plain normal vectors, we had to use reverse floating point depth. The rasterization algorithm is similar to previous state-of-the-art and consists of 4 compute shader stages: setup and cull, coarse raster, fine raster, and final resolve to bit fills to lists. In the setup and cull phase, a compute shader thread is dispatched for each hexahedra in the scene. We can't render faces close or behind the camera, so this stage clips the hexahedra at the near plane. Because we are not using a scanline rasterizer, other clip lanes can be ignored. The resulting hexahedra is emitted in a packed struct and contains the vertices together with side and edge indices. Here we also classify if vertices and edges are front or back facing. This is needed later to determine the depth bounds during rasterization. If the hexahedra is clipped, the new side is removed. The rasterizer can determine that the camera intersects with the hexahedra because there are only back-facing faces instead. The clip stage also computes screen space tile bounds and emits work for the coarse raster stage. For each hexahedra, we want to check each tile that is possibly intersecting based on rectangular screen space coverage. Bitting hexahedra into each tile and then running a thread for each tile with an 8x8 thread group works, but can be very slow if a lot of small hexahedra are on screen due to very bad thread utilization. Up to 63 threads can be idle in those cases, and we saw scenes with several milliseconds spent on rasterization. What we ended up doing instead is emitting work for 1 thread per hexahedra and potentially covered tile into lists that are consumed by the next stage via indirect dispatches. This way, for example, 64 hexahedra, each covering only 1 tile, will still fill a thread group. Each thread in the coarse raster stage then processes 1 potentially covered tile of a hexahedra and checks its 256 by 256 pixel region for intersections. If there is an intersection, we also bin into clusters, which are also 256 by 256 pixels in screen size and 24 layers deep like in Doom 2016. For each cluster that is intersecting the hexahedra, we set a bit in a per cluster bit field. This already gives us tighter binning fit than the CPU path we used in ITTech 6 because the CPU used an approximation for the intersection of hexahedra with the cluster frustrums. This stage also produces the work for the fine raster stage. Again, we emit 1 thread for each hexahedra and fine tile. Each coarse tile has its own work list. This allows us to get slightly tighter bounds because the fine raster rectangular screen coverage is computed for each of those coarse tiles. As the final raster stage for each fine tile covered in each coarse tile work list, we emit 1 thread that will determine if the hexahedra intersects a 32 by 32 pixel tile. Because all faces are processed together, we can accurately determine the min and max value of the entire hexahedra. Earlier in the frame, we conservatively downsample the depth buffer into min and max values for each 32 by 32 pixel tile. We can therefore determine if the min-max range of the hexahedron intersects with the min-max range of the depth values. If there is an intersection, the hexahedra is marked as visible for the fine tile by setting a bit in the per tile bit field. For point lights, we also do an additional approximate sphere versus tile frustum intersection to get a slightly tighter fit. After all the rasterization stages are done, we resolve the bit fields to lists of indices because it would be inefficient to scan a bit field in each fragment shader invocation. Instead of running 1 thread per bit or 1 thread per tile, we run a thread group with 64 threads for each tile. Each thread group checks 64 bits in parallel and uses subgroup ops to compact the resulting index list. After all bits in the bit field have been processed, one of the threads in the thread group writes the final light count. We notice that with only checking tiles for opaque geometry, the results can be bad for parts of the screen with large depth discontinuities. Here we see the light overdraw if the fragment shader is only using tile lists. As you can see, for the tiles that have to cover both the teeth and the background, there is a large difference between minimum and maximum depth values. The rasterizer has to bin any light that intersects this depth range, which causes a lot of entries in the lists. To mitigate this, we check both the tile and the cluster for each opaque fragment shader invocation and select the list which has fewer entries. As you can see, this results in significantly fewer lights to consider overall. Here we visualized which pixels choose the tile or the cluster light list. In green parts, the fragment invocations are using the tile lists, while for blue parts, the fragment invocations are using cluster lists. An optimization introduced in Doom 2016 is to use the scalar units of the AMD GPUs in the consoles to read light and decal parameter data. This requires that all threads in the fragment thread group process the same light or decal lists. To do this in ITAC 6, we just checked if all threads in the thread group are using the same cluster, and if that was the case, we assumed that all threads are using the same decal or light list. But now, with tile binning, there are many more tiles in screen than we had clusters in ITAC 6. Here we can see a visualization of the uniform thread groups in green and the non-uniform thread groups in red. This is the result with just checking the tile ID to determine if the lists are uniform across the thread group. With this approach compared to clustered, there are therefore a lot more thread groups which are not scalarized. To reduce this problem, we compute a hash of the light list for each tile in the bit-filled resolve compute shader and store it with the number of lights for each tile and cluster. Then, instead of checking for uniformity by tile ID, we check if all threads in the thread group are accessing a list with the same hash. The picture here visualizes the hashes with the color picked by each hash value. As you can see, large screen areas have the same hash value. And this is the same visualization before, but checking for uniformity by hash. Many more threads are now completely uniform, and this even works if a thread group accesses both tiles and clusters if they have the same list hashes. For each of the stages, the threads are running for a lot of cycles. For example, the rasterization threads need to test each hexahedra's face, sides, and vertices against the tile. Where there are a lot of hexahedra, the raster resolution is quite low. This causes the situation that even on the Xbox One, the GPU is only partially filled with just rasterization work. One of the obvious ways to better utilize the GPU at the same time is to overlap with asynchronous compute. We run, for example, the last frame's post-process in parallel. On the other hand, we notice that adding more hexahedra has almost no impact on the total runtime of the rasterization. At the same time, the gameplay team needed a way to know if certain objects are visible or not to deactivate some costly CPU calculations. What we ended up doing was to run the bounding boxes of those objects through the binning rasterizer. Instead of testing for intersection with the depth buffer in the fine raster stage, we check if the hexahedra is in front of the conservatively downsampled depth buffer max values. If it is visible, we tag a bit in the bit field that is read by the CPU next frame. This was fast enough for thousands of visibility queries which are essentially free. The next topic that I will talk about is geometry decals. Geometry decals are small decals that are authored as part of the mesh. Our artists requested this feature to reduce texture consumption and increase fidelity. Our challenges were that we wanted to spend very little extra frame time on this. Our renderer is also forward, so we can't just blend decals on top of the G-buffer, and even if we could, it probably would be too slow. As an example, you can see a screenshot of an asset in the game without geometry decals. And this is what it looks like with geometry decals enabled. There are many small details added without increasing the base texture size. The solution we came up with is to create a hybrid of projected and mesh decals. The idea is that we can compute projection matrices from world into texture space from the mesh UVs and positions. Because world space to texture space is unique for each mesh instance, we instead store object to texture space matrices on disk. At runtime, the world to texture space matrices are computed by multiplying with the object's model matrix. This also means that each instance needs its own memory for each projection. To render the projected decals, we render indices into an R8 buffer after the depth pass. We set the depth compare mode to greater equal, so decals behind opaque geometry will not be rendered. To avoid C-fighting, we also apply a small depth bias. A limitation is that to avoid wrong assignment of decal indices, the decals need to be authored coplanar to the mesh geometry they are projecting onto. This is very fast because we only need to write one R8 channel. Additionally, the geometry doesn't have a lot of triangles and it usually doesn't cover a lot of the screen. Even on Xbox One, we can typically do this in about 50 microseconds. Finally, in the forward shaded fragment pass, we can read the geometry decal index from the R8 buffer and index into the list of projections that is bound for each instance to reconstruct the texture coordinates. Because the decal is applied in the fragment shader, we can do arbitrary blending with the decal values on top of the underlying material. Here is a typical scene with a lot of hard surface objects, but with geodecals disabled. And here we see what it looks like with the geodecals enabled. This is a debug view of the geodecal index buffer for the same scene. We typically have thousands of them on screen for this kind of scenery. Our geodecals are virtually free in terms of render time, but there are some limitations. Because we are using an R8 buffer for the indices, we are limited to 254 projections per mesh. Note that not each triangle necessarily needs its own projection. If the texture space is continuous and the decal geometry is flat, the projection can be shared between multiple geodecal triangles. On the other hand, if the decal geometry is bent, there will be a lot of extra projections, so curved decal geometry runs out of projections quickly. As mentioned before, we also need storage for each projection per instance. We currently allocate a pool of 1 million decals, which corresponds to 32 megabytes. Because there needs to be some defined order, we currently always apply geodecals first. Animated geometry is especially tricky because it requires recalculation of the world to texture space projection matrices on the fly. To do this, we run compute shaders. Because there are usually few animated projections, this is very fast. In the video, you can see an animated asset with geodecals. Moving on to geometry caches. Geometry caches are canned animations that we compile from Alembic caches. This is based on work I did for a different project before id Software. The animations are streamed on the fly from disk because loading it into memory would be too much data. Compared to the old implementation, there is improved compression due to the addition of prediction frames and hierarchical B-frames. Additionally, motion prediction can be forward and backward, and we use CryENGINE for the final bitstream compression of the prediction. Another advantage of the new system is that multiple instances of the same geom cache can share streamed data blocks in memory. We not only support animation of positions, but also colors and UVs, which is used for effects. To reduce data rate further, we added automatic skinning based on Ladislav Kavan's work presented at SIGGRAPH 2010. The algorithm automatically creates a skinned animation consisting of a base pose, bone assignment, and the bone matrices for each frame. To fit into the geometry cache framework, we quantize the bone matrices and apply the same prediction and compression like we do for the other streams. Automatic skinning does not always work well for all animations. For example, there can be visible cracks if two parts of a mesh need to exactly align. For those cases, we still support regular vertex animations. In the example on the right, the regular animation takes up 9.3 megabytes of disk space, while the skinned animation with 63 bones only uses up 2.8 megabytes. For quality reasons, we want to pre-compute tangent frames for each frame and stream those too. Storing this naively as 2 3-component vectors is expensive in data rate. Instead, we are storing the normal as 2 bytes with octahedron normal encoding and another byte for the rotation around that normal for the tangent. 2 bytes octahedron encoding appears to be good enough for the vertex normals. After trivially decoding the normal, to decode the tangent, we first need a deterministic orthonormal vector which we can rotate around the normal. Using a cross product with, for example, the x-axis vector causes singularities if the normal vector is too similar. Instead, we pick an orthonormal vector based on the absolute values of the x and c component of the normal as given by the first formula on the slide. Finally, we can reconstruct the tangent by rotating the orthonormal vector with Rodriguez rotation formula. The last term of the formula cancels out because the vectors are orthonormal, which gives us the second equation on the slide.
Hi, my name is Geffroy and I'm a principal engine programmer at id. I will now briefly talk about how we use and implemented material blending in Doom Eternal. Material blending is typically the first step to add detail to the world. It precedes the decaling pass in the levels. Material blending happens often as part of the prop building process, for example, to add a layer of grime to a model that's going to be used in numerous locations. It can also happen during level building for environment-specific effects, such as adding snow or moss on some specific instances of a model. It is implemented by simply blending full material stacks, meaning the albedo, normal, specular, smoothness, and emissive channels. The blend weights defining the influence of each material most of the time come from vertex painting. We, however, also have the ability to use dedicated texture maps to drive the blend weights when the tessellation level doesn't match the required granularity. This is mostly the case for characters and some organic assets. Artists can use either approach depending on the situation. The blend weights are also modulated at runtime by material height maps. This has higher frequency detail to otherwise potentially very coarse blend weight data and respects physical features of the underlying materials. The vertex painting process itself is done using a dedicated internal tool. It allows for up to 4 materials per asset with a maximum of 2 materials per triangle. One challenge with vertex painting is that LOD generation can potentially decimate vertices containing very perceptible paint information. This typically results in very noticeable LOD popping. For this reason, even though large zero of all painted instances of the model is shared, lower quality LODs are made unique with painting. The memory overhead was manageable thanks to a limited set of paint permutations per asset and the heavy use of decals for location-specific detailing. As an example, here's a screenshot of an environment of the game showing only the base material and model. And here's the result of a vertex paint pass adding a layer of grime to the base materials. On this screenshot, you can see how the use of material height maps drives the accumulation of snow in the crevices of the base material. The base geometry is very coarse, and therefore so is the vertex painted data. The height maps thankfully help get some high frequency and physically plausible detail. Material blending is also used on characters to add tiled, high frequency detail, such as skin pores. And here's another example of material blending used on characters. Here's a close-up shot of a cacodemon. The next thing I want to talk about is how we dealt with the large increase in on-screen geometry compared to Doom 2016. We have a budget of roughly 3 times the triangle count, but have to run at the same speed on the same hardware. One key tool to achieve this was GPU triangle culling. The idea is to run a compute shader early in the frame, which will remove invisible triangles and generate an indirect index buffer containing only the surviving geometry. This removes pressure of the graphics hardware pipeline, since we don't have to run useless vertex threads, which can easily cascade into many subtle performance issues on GC and hardware. The compute shader performs backface, frustum, and microtriangle culling in a manner very similar to what was described by optimizing the graphics pipeline with compute for Frostbite. The main difference on the culling front is that for occlusion culling, we generate a conservative depth MIP chain based on the software occlusion buffer provided by Umbra for CPU culling. Triangle culling runs in addition to the standard CPU culling process. Overall, in most scenes, it removes about 70% of the geometry that's been submitted for rendering. With a budget of 3 million visible triangles after CPU culling and LOD selection, only 1 million triangles make their way to the graphics pipeline. GPU triangle culling on its own did not solve all the challenges introduced by the much more complex levels we have in Doom Eternal. Our levels are built of a large amount of instantiated models, and it is possible to have up to 15,000 of those in view. Those models, especially those in the distance, which are being rendered at lower LOD, can be fairly low poly. This can result in a lot of unused vertex shader lanes in addition to significant command processor overhead when passing the draw calls. Altogether, it can result in really poor GPU occupancy. Issuing 15,000 draw calls, even with a very tightly optimized loop, can also cost a significant amount of CPU time. This is even worse when you have to run a depth3 pass in addition to the opaque pass. Our idea here is that we could leverage the concept of dynamically generated index buffers to automatically merge many models in a single optimal buffer, which would be rendered in a single draw call. Coupled with GPU triangle culling, this results in close to 100% useful lanes in the vertex shader, no hardware triangle rejection, and better GPU occupancy overall. This idea of dynamic geometry merging on a GPU relies on a few constructs. First, all the geometry that we're going to be merging has to be using the same pipeline state. This is something that definitely works best when you rely on very few Uber shaders rather than thousands of permutations. which is a guiding principle that we've been following for many other reasons anyways. Different materials can be merged together. The only requirement here is that all merged models have to use the same pipeline state. We also rely on a completely bindless GPU pipeline. This means that all resources are globally indexable by our shaders without needing, for example, to bind specific textures or buffers for a given draw call. There are three main components to this. All our vertex data is allocated from a single large pool. This is a requirement that is consistent with our geometry streaming implementation anyways. All our textures can also be globally indexed. The image streamer maintains a list of global texture descriptors as we stream them in or out. Finally, all the uniform buffers are also allocated from pools, with one dedicated pool for each pipeline layout supporting geometry merging. In practice, we only have three indexable layouts in Doom Eternal: one for the environment, one for characters, and a third one for geometry caches. At runtime, when a CPU traverses the scene to gather the list of visible meshes, we assemble them into geometry sets. Up to 256 meshes sharing the same pipeline state can fit in one geometry set. At this point, we also reserve some indirect index buffer space for each geometry set. We then issue one GPU culling dispatch call per geometry set. The culling shader outputs a merge index buffer containing only the visible triangles for the whole set. When writing the index buffer, we combine the vertex ID and mesh instance ID into each 32-bit output index. This will make it possible to fetch instance data when running the geometry. It also guarantees correct behavior when it comes to hardware vertex reuse. When it comes to rendering, we only have to issue a single draw call per geometry set. This effectively renders up to 256 meshes at once. In the vertex shader, we extract the vertex ID and instance ID from the packed index buffer value. The instance ID is used to resolve all per instance properties. This includes, for example, the base offset to fetch vertex data from the global pool, as well as the per instance uniform buffer offset. The uniform buffer, in turn, contains all global indices to access any sample texture, along with any other shader constant. We also need to ensure that divergent access to textures and buffers is scalarized. Depending on the platform, this is done using an explicit scalar loop or a built-in keyword, such as the HLSL non-uniform resource index. It is worth pointing out that shaders supporting dynamic merging also support the standard non-merged code path. This is useful for A/B testing, but also to handle overflow of the indirect index buffer. For this purpose, we have our internal shader preprocessor generate both a standard and a mergeable version of those shaders. The mergeable version will implement the adjustments that I've just described, meaning buffer fetches instead of vertex attributes, additional indirection for instance data, and scalarized loops for divergent fetches. Something worth mentioning is that the CPU code preparing the buffers for GPU culling and merging is embarrassingly parallel and is simply part of the scene traversal. It also effectively removes most of the API overhead you get from preparing and issuing individual draw calls. When it comes to GPU scheduling, the culling and merging shader runs in async compute. It is issued before our shadow pass and will therefore run in parallel with it. Considering that we handle the GPU queue synchronization per geometry set, depending on the complexity of the scene, it may also be possible to have some overlap between culling of a geometry set and rendering of another set. Finally, by nature of this merging process, all instance data fetches in our rendering shaders are now potentially divergent. This may sound scary, but is actually a non-issue, considering that almost all of those fetches are happening either in the vertex shader or outside of the hot paths in the pixel shader. Other savings largely make up for the added divergence there. To demonstrate this, here's a screenshot of a typical combat space. The construction of the scene heavily relies on the use of instantiated models. In some levels, we can have up to 15,000 in view. And here's the debug rendering mode, allocating a unique color to each mesh in the scene. It's worth pointing out that enemy models are often composed of many different surfaces, even more so in combat when you trigger wounds on them. And here's another debug rendering mode, allocating a unique color to each geometry set, meaning to each draw call. You can see that the entire environment can be rendered in just very few draw calls. In particular, you can see that all the characters, meaning the arachnotron in the forefront, but also the imps fighting in the background, are all rendered in a single draw call. Overall, GPU triangle cutting and merging save up to 5 milliseconds of GPU time in some of the heaviest scenes of Doom Eternal. There is close to no waste in geometry processing on the GPU. Almost all vertex threads are active, and close to no triangles get rejected by the fixed function pipeline. We're also seeing significant savings on the CPU side. Instead of 2 draw call heavy passes for depth and opaque, we now have some simple buffer setup code happening during our visibility scene traversal. Now I would like to give a brief overview of our goal system. One of the essential goals was to provide satisfying feedback to the player by having clear silhouette changes as enemies take damage. This was achieved by modeling individual wounds and revealing them at runtime. Each wound mesh is authored alongside with a clip and blood mask. The clip mask is used to discard the geometry of the base material that would otherwise cover the wound. The blood mask is used by the character shader to drive the blend weight of a tiling blood effect. With potentially more than 12 active wounds per character and 16 active enemies in a fight, each composed of multiple base materials, we potentially end up drawing a lot of mesh parts. This thankfully works seamlessly with the GPU triangle cutting and merging process described earlier. The most complex characters can have up to 30 different wounds. This would be too much to sample at runtime. We avoid this by caching the state using a dedicated buffer with a single byte per vertex per character instance. We pack into each byte both the current clip weight and the blood weight, and update the values as wounds are getting applied. On top of that, we can also contribute to the blood weight on any bullet impact, even if it doesn't trigger the mesh wound, in order to give immediate feedback to the player. The vertex and pixel shaders then only have to sample this buffer once, which is naturally a lot more efficient. And here you can just see a couple of additional examples of dramatic silhouette changes occurring during a fight.
Now I will talk about the water rendering in id Tech 7. First, we generate a displacement map to use for the water surface. We use the technique described in Simulating Ocean Water by Tessendorf 2001. How this technique works is by generating a random spectrum for the surface waves in frequency domain using a semi-empirical model called the Phillips spectrum. Then we perform an FFT using compute shaders to transform the frequency domain to displacement vectors, resulting in a tileable displacement map. The output displacement map for us is 256 by 256, but it can really be any resolution independent of the other water passes. Finally, we generate a normal map from the displacement map using finite difference between neighboring texels. To generate the actual water surface mesh, our technique is based on the projected grid concept introduced by Johansson 2004. Instead of tessellating the water plane directly, this technique projects a screen space grid mesh along the view frustum onto the water plane, then displaces those projected grid vertices in world space. The next few slides will go into detail of our implementation of this. First, we render the water planes to a depth buffer that has the same resolution as the screen space grid we plan to use. In our case, this is 256 by 256. And because their resolutions match, each depth buffer texel corresponds to a screen space grid vertex perfectly. Next, we do a compute pass over the depth image. For each depth texel, we compute its world position from its depth. This corresponds to projecting the screen space grid onto the water plane. At this point, we apply the displacement from the displacement map to that world position. The displacement map is simply tiled in the world XY plane. At this point, we also apply additional displacement from water hit ripples from, for example, shooting the water. How this displacement is calculated is explained in a later slide. So the output of this pass is the vertices image, where each texel contains the final world position of the corresponding screen space grid vertex after that vertex has been projected onto the water plane and displaced. The vertices image is temporally accumulated with the vertices image of the previous frame to avoid aliasing the displacement map due to the low resolution of the vertices image. Finally, we rasterize the screen space grid. In the vertex shader of this pass, each vertex simply looks up its corresponding texel in the vertices image to obtain its world position. Any grid vertex that's not actually over water will have its position set to not a number in the vertex shader. for example, 1 divided by 0, and that causes the whole triangle to be dropped. The output of the screen space mesh rasterization is the water G buffer, which contains the depth and normals of the water surface. This will be used to light the water surface later. The G buffer is 1/2 of the screen resolution, 1/2 horizontal resolution specifically, to reduce the number of lighting computations needed later. In the mesh rasterization fragment shader, normals are computed using finite difference instead of the normal map we generated earlier. This is because that normal map we generated does not account for water hits. That normal map is used instead to further perturb the normals to give the water additional bumpy detail by making the perturbation small and tiling it at a much higher frequency than the displacement map. In the previous slide, we mentioned while rasterizing the screen space grid, we drop triangles which have any non-water vertex. As a result, this gives a stair-step appearance to the water edges, as you can see in the image on the left of the slide. Because we don't want these stair-step edges visible, artists must hide all water plane edges behind opaque geo. Finally, we also do conservative depth culling in the fragment shader. We compare the water fragment depth against the max tile depth, and if it's greater than, we just discard that fragment. Here's a video visualizing the screen space mesh that gets rasterized. In this scene, we actually have multiple water planes, but there's just still one screen space mesh for all of them. And this is what it looks like with just the water surfaces rendering. And on the edges of the water planes, you can see the stair-step artifacts we mentioned. And these are the stair-step edges that artists must hide behind world geometry. Previously, we mentioned how there was temporal accumulation on the vertices image. The reason for that is shown in this video. With the temporal accumulation disabled, you can clearly see the screen space grid sort of moving underneath the water surface, causing this shimmering. And here's what it looks like with the temporal accumulation enabled. As you can see, when the camera pans, the shimmering is much less noticeable. Now, before we do the final lighting pass on the water surface G buffer, we compute the water surface SSR, screen space reflection, in a separate pass to a separate render target for the purpose of doing temporal accumulation on just the SSR. This increases the sampling rate and reduces fireflies in the SSR image, and this is also done at 1/2 horizontal resolution. Finally, we compute the water surface lighting from the water G buffer. Lighting the water surface is slightly different from our usual lighting. We do an optimization on the ambient component where we compute the ambient lighting per screen space mesh vertex instead of per G buffer pixel. And this is done by computing the ambient lighting in the vertex shader of the screen space mesh rasterization pass and storing the interpolated result into the G buffer. So our water G buffer actually contains depth, normals, and ambient lighting. For the diffuse component, instead of using our usual diffuse BRDF, we used a Haney-Greenstein phase function to simulate water particulates scattering at the water surface. And this component is also scaled based on the water depth. So in this example scene, the deeper water will actually appear more red, whereas shallower water will appear more clear. And also we have a constant color emissive component that the artist can just set, and this constant emissive component is also scaled by the same depth factor, so that deeper water is more emissive, shallower water is less emissive. The final water surface lighting is output to a 1/2 horizontal resolution buffer, and it contains the final water surface lighting as well as the water surface alpha, which we need during the final compositing step. All the water passes I've described so far occur right after our rendering pipeline has rendered all opaque surfaces to the main color buffer and before it has rendered any transparent surfaces. The pass described in this slide is the last water pass to happen before we start rendering transparent surfaces. And what this pass does is it takes the main color buffer, which currently contains all the opaque surfaces, and it splits it into two buffers, a before water and an after water buffer. And the before water simply contains all the pixels that are before water, and after water contains all the pixels that are behind the water surface. And the reason for this is because eventually we want to distort the pixels in the after water buffer to simulate water refraction. And the way this pass works is very simple. We simply look at the main depth buffer for the depth of each pixel and compare it to the water G buffer depth to see if a pixel is before water or after water. Now our rendering pipeline will render all transparent surfaces. But now that we have these two different targets, before water and after water, instead of just one main color target, all of our transparent shaders had to be modified to handle this. So basically, if there is a water surface visible, it will check the final fragment depth against the water surface G buffer depth to see if it falls before water or after water, and then blend that fragment to the appropriate target. So it turns out, in addition to the before water and after water buffers, we actually need one more buffer, which is the before water alpha buffer. And this buffer simply keeps track of the alpha of all the transparent surfaces that we blend into the before water buffer. We need this because before water transparent surfaces might end up directly in front of the water surface, in which case its alpha needs to be tracked. So during the final composite, we can correctly blend these transparent surfaces on top of the water surface. After rendering all transparent surfaces, it's time to do the final composite. We blend the after water buffer, the water surface buffer, and the before water buffer in that order, which is back to front. When reading the after water buffer, distort the text chords to give the appearance of water refraction. This technique is described in SUSE 2008. The amount the text chords are distorted is based only on the water surface normal, which we have from the water G buffer. And this is a non-physically based distortion. Additional water displacement from water hits is simulated on a height field texture centered around the camera, which moves around with the camera. The simulation algorithm used is described in Muller-Fisher 2008. Each frame, the simulation time steps forward from the previous frame height field to get the current frame height field, with the previous frame height field fetched using reprojected text cores to account for camera movement. The position of the height field grid actually snaps to multiples of the grid cell size when moving with the camera, and this ensures that the reprojected text chords, when fetching from the previous frame height field, always falls exactly on the texel center, so introducing no additional linear interpolation. Here's a video showing the water hit ripples. For water caustics, we generate a tileable caustics texture from the water displacement map. We do this by rasterizing a grid mesh where each grid mesh vertex is aligned with a displacement map texel. And for each vertex, we shoot it at the displacement map and compute its refraction direction and then follow that refracted direction to some constant distance. So basically, the whole mesh is shot at the water displacement map and refracted to some constant distance, thereby distorting the mesh as if it's been refracted through a water surface. The exact implementation details can be seen in the source code on this slide. The resulting caustics texture is used in the next frame and projected onto all the scene geometry that's underwater or right above the water. It's incorporated into our main lighting code so that it projects onto every surface, and it's also incorporated into our light scattering pass And this allows us to get underwater god rays resulting from the caustics texture. Here's a short video showing what the water caustics looks like. One additional feature we added was the support for flowing water, such as waterfalls or streams and creeks. How we accomplished this was we would rasterize the flowing water surfaces directly to the water G-buffer, and the water surface normals would be perturbed using a normal map and a flow map authored by artists. And these flowing water surfaces actually had no displacements applied, and this is room for improvement. So they just rendered directly to the G-buffer with perturbed normals. And here's a video showing an example of a flowing water surface. In this particular example, the flowing water surface is just a flat plane. There's no displacement of any kind applied to it. It's just normals and a flow map. And to wrap up my presentation on water rendering, I'll show you some sample scenes from the game. Now, this one has an emissive component, a blue emissive color. It looks really nice. This blood water from our Super Gorness level. And that's it. Thank you very much.
This ends our presentation for today. I hope you enjoyed it and learned something. Special thanks to our colleagues at id Software and our friends at AMD and NVIDIA.